We're going to continue talking about microwave background radiation in the universe. Well, Penzias and Wilson discovered with their weird horn-shaped antenna in New Jersey that there was this background radiation that came from all areas in the sky, all times of years and all directions. And that was proof that the Big Bang Theory probably had some merit. The question is always, where did that come from? Okay, it's out there. Yes, it's coming from all directions, but where did it come from? From our understanding of the Big Bang, the early universe was very, 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 very hot. Very dense, and opaque. Now, what do I mean by an opaque universe? Meaning there was no light. And the reason there was no light is because of the fact that in the early universe, all there were particles. There were protons and there were electrons, but you have to have electrons actually orbiting around protons in the nucleus of a hydrogen atom in order for light to be created. And in the early universe, it was so hot that it was opaque. We could not see through it. So this occurred for about the first 380,000 years that we couldn't see anything. If there was something from before that period of time, we couldn't detect it with electromagnetic waves because the mechanisms to make electromagnetic waves didn't exist at that point in time. So this 380,000 years after the Big Bang is actually the limit of how far back we can see in time when we look at old light. If there was something to see prior to that, our instrumentation is good enough, we could see it. So this is the boundary of the observable universe. At about 380,000 years after the Big Bang, the universe got cold enough, it actually expanded far enough that electrons and protons could bond and form atoms. When that occurred, that is called the period of recombination. Protons and electrons formed these hydrogen atoms, and you have to have those atoms produced before you can get light, because light occurs when an electron gets excited, jumps to a high energy level, falls back down, and then you get a photon of light. So you have to have atoms in order to have light. We're going to look at a picture similar to this very often. This is a image kind of explaining or trying to describe all of the different periods of time in the Big Bang. So there was the early universe. And about, this drawing says about 400,000 years. The previous slide said 380,000 years. But that was the point in time when there was a recombination of atoms and then light was produced. And then each one of these different parts we will discuss in the next sections. Oh, there it is. Now, where did this microwave background radiation come from? This opaque wall that was the beginning of light in our universe. When it existed, the universe was small enough that it had a peak curve. The whole universe had a black body curve with a peak around 3,000 degrees Kelvin. It was very, 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 very hot. What's 3,000 Kelvin? That is about the surface of our sun. Okay, so that is, the entire universe was that hot at the beginnings when we could actually see light. Prior to that, it was so hot we could see no light. Now today, the universe has expanded to the point where the black body curve, due to the expansion of the universe getting bigger and bigger and bigger, so that the peak of the universe's black body curve is about 3 degrees Kelvin. 3 degrees Kelvin is 3 degrees above absolute zero. That is incredibly nutty cold. And we've gone from a universe that is as hot as the sun everywhere to a point where our universe is as cold as almost absolute zero everywhere. Well, how the heck did that occur? Because that little 3 degrees Kelvin, that's the microwave background radiation that Penzias and Wilson discovered. Okay, here's an analogy to try and make sense out of this. Let's say I have a cup of boiling water. So I've got 1 cup of water, 100 degrees Celsius. I've got a lot of energy in a very small space. This is sort of like it was right after the Big Bang. Very condensed, very small universe, lots of energy in a tight space. As the universe expanded, imagine that you take this cup of water and you fling it on a sidewalk, or you fling it on a driveway. As the water gets spread out to cover a very large space, what happens is it cools very quickly. And the heat gets dissipated. Instead of being in a very contented small wad, the heat is spread over this huge, huge area. So you've got the same amount of heat, but the heat is now spread over such a big area that with this big area, it is cooler everywhere. Okay, I hope that makes a little bit of sense. Now, continue with this crazy puddle analogy. When astronomers look at the background radiation from space, the microwave background radiation, it's sort of like if we had to analyze a puddle and then recreate the cup of water. From analyzing the puddle, we'd have to ask questions like, how much water was there originally? So in the Big Bang, we ask questions like, how much heat was there originally? Is it evenly distributed? Are some areas deeper and some areas thinner? We ask the same sort of questions when we talk about the universe. Is the heat distributed evenly, or are some areas hotter and some areas colder? And then the big question is, what caused the water to be thrown out? What caused the explosion? What caused the expansion of space itself? Well, to try and answer some of these questions, back in the early 1990s, there was a satellite that was put up by NASA, and it was called the Cosmic Background Explorer, commonly referred to as the COBE Satellite. The COBE satellite's job was to do pretty much the same thing as Penzias and Wilson's weird kind of horn-shaped antenna, but it was going to do it a lot more high-tech and above the Earth's atmosphere. So what they were looking for are those residual little dribbles of energy left over from the Big Bang. Due to the work of Penzias and Wilson, they knew what signal to look for. They're looking for a black body curve that is way over here with about a 3-degree Kelvin peak. And that's what they started looking for, is small fluctuations in heat in the entire universe. Well, the first COBE map that was produced in the early 1990s, if you look at that, you're going to go, that's not a terribly sophisticated map. But what it showed, due to slight differentiations in temperature and different Doppler shifts, what the first COBE map showed us was this. The red band in the center, that's our Milky Way. That's this hot area that's really close to us and nearby. We can detect areas that appeared to be hotter. The wavelengths were Doppler shifted to a higher energy. And that is because this is the part of the universe that is actually moving towards us. The areas that are orange and yellow up here are actually parts of the universe that are moving away from us. And we could tell with our, back in the 1990s, we're talking 30, 40 years ago now, that parts of the universe were moving in different directions. And we could detect the sun's revolving motion around the Milky Way, the fact that the Milky Way itself is moving within our local group of galaxies, and the local group, our local cluster of galaxies, is actually moving with an expanding universe. We're going to talk about more detailed pictures of the universe in the next section.